In this video, we're going to talk about how to find area of triangles. And I know what you're probably thinking. Why are we discussing how to find area of triangles when this is a skill that you probably mastered maybe back in 5th grade, that the area can be found using half the base times the height. And the real key, the only key, of course, is that the base and the height are measured perpendicularly. Well, the reason that we're looking back is we've learned a little bit more now. And we've learned some trigonometry. And what that means is we can kind of ditch this notation about base and height and measurements that must be made perpendicularly and start thinking about how you could use sine and cosine and other properties to find the area of triangles in maybe a quicker way depending on the information that you're given. So suppose that our triangle had vertices, just say A, B, and C, so that the base was little a, and this side over here is little b, and then this side is little c. If I wanted to find the area of this triangle in maybe a different way, I could think about how the height of this triangle is related to the sine function. So here's my height. I'll just call it h here. And if I focus in on this triangle on the left, this right triangle that's formed by that altitude h, then it's pretty clear that the sine of angle B, let's get that again there, sine of angle B is equal to h over c. So h is equal to c sine B. Of course, I could have instead focused on this right triangle on the right over here. And in that case, I would have thought about h as another possibility for h being b sine c. So what that means is I have two different ways I can think about the area of this triangle just through this height that I found on the altitude. And that is area is equal to half the base, which is A, multiplied by the height, which is B sine C. And the other possibility is 1/2 the base, which is A, times the height, which is C sine B. And both those formulas have a nice little ring to them. 1/2 AB sine C, AC sine B. Another possibility, if I drew a different height, would be 1/2 BC sine A. All those are nice, quick ways we can find the area of a triangle, and all of them originate from a side angle side setup. And that's clear because you have side A, side B, and then angle C, or side A, side C, and angle B, and so on and so forth. So that's a quick way we can find the area of a triangle. Let's look at a quick example where that would be useful. Let's say I had a triangle and I want to find the area. And the triangle has a side of 8, another side of 5, and an included angle between them of 30 degrees. And I want to find this triangle's area. So I don't know its height, and I'm not going to even try to find it. I'm just going to say area is equal to 1/2 AB sine C, and it's important for A and B to be sides that border the angle. So let's just see how that would work here. So if I put my vertex A here and my vertex B here, then 8 is little a, 5 is little b, and oh yeah, look, angle C is over here at 30 degrees. So it's just a matter of, I'll write area here so the A's aren't confused, plugging everything in. 1/2 times 8 times 5 times the sine of 30 degrees, and well, sine of 30 degrees is also a half. That's convenient. So I'll have 1/2 times 8 times 5 times a half. So that's 40 divided by 4, so the area would be 10 units squared. If I were to make a little change to that problem, let's just say, for example, that the 5 were over here on this side instead. Let's say that the 5 was side C. This problem, oh, who would create such a problem here? This problem is a ambiguous case because it's a side-side angle setup. So this one wouldn't be quite as simple. In fact, there were 2 possible areas on this side, and I'll invite you to think about what they might be. What you'd have to do in order to solve them is figure out the 2 possible measurements for angle B. I could have a triangle set up like the one I originally drew, or I could see one that maybe looked like this instead, where angle A was obtuse and angle B was acute instead of the other way around. So I'd have to find the 2 different measurements for angle B, and then I could use 1/2 8 times 5 times the sine of angle B in order to solve. Let's look at one other possible setup that is much more common than finding areas of ambiguous cases. Let's look at a triangle where 3 sides are known. So in this case, I've got an 8, I've got a 5, and I've got a 7, maybe, something like this. And I want to find the area of this triangle. This is probably what you'd think of as the typical case, not a textbook kind of problem where they tell you the perpendicular height, but instead you have some triangular region, you measured its sides, and you just want to know its area. So this is going to be a matter of finding an angle. If I can find an angle, then I'm free to use 1/2 AB sine C in order to solve the problem. So let's just label the triangle ABC like this. And I'm going to try to find angle C. And the way I'll find it is using the law of cosines. The law of cosines is helpful here because I know 3 sides in the triangle. So c squared equals a squared plus b squared minus 2ab cosine of c. So I want to know angle C here, so it's going to be worth actually solving this equation for angle C, or maybe even the cosine of angle C. If you haven't done this before, I recommend trying it. You'll isolate cosine of C, and you'll find that it's equal to a squared plus b squared minus c squared divided by 2ab. And that tells me that this angle C measurement that I have right here could be found by using the cosine inverse of 5 squared plus 7 squared minus 8 squared divided by 2 times 5 times 7. And you can check me on this, but this tells me that the measure of angle C is equal to 82 degrees. And I should point out that the reason that I used the cosine law to find angle C here and not angle A or B was there was a chance that angle C was the obtuse angle in the triangle. It was definitely the largest angle in the triangle. So using cosine to find it is worthwhile. Sine will hide the obtuse angle since inverse sine will always give you acute solutions. Okay, so, well, what's the point? The point is that I want to find the area of this triangle, and now I can do it. So the area of the triangle will be 1/2 the base times the height, or 1/2 AB sine C. So in that case, it'll be 1/2 7 times 5 times the sine of the angle between 7 and 5, which I just found to be 82 degrees. So that gives me an area of 17.3 units squared. It brings up another question, though. If it was possible to find the area of this triangle using only the side lengths, why don't we have a formula for that? Why wasn't there a way to simply take 8, 7, and 5, no angles at all, no perpendicular heights whatsoever, and punch them all into a formula, some maybe magical formula, and get directly to the answer. This was a question that has been around since the first century, and a gentleman by the name of Heron of Alexandria solved this problem, and he used something called Heron's formula. Well, I guess that's what we call it now. I don't know if he named it after himself, or I guess we probably named it after him. And Heron's formula is a way to say, okay, half base times height, that's nice, but I need to know the height perpendicularly. And, well, 1/2 AB sine C, that's kind of new, and maybe you'll like it or maybe you won't, but why do we need to know angles and trigonometry and all that stuff? What Heron came up with was a new formula, an entirely new formula, that is going to take only the sides of the triangle and punch them in just the right way, and it'll calculate the area. And his area formula looked like this: S times S minus A times S minus B times S minus C, all under a radical, will give you the area. But what's S? What does that have to do? Do we have to calculate something new? Not really. S in Heron's formula is called the semi-perimeter. And it is exactly what it sounds like it is. It's half of the perimeter, so it's A plus B plus C over 2. S was a convention that he used to make the formula much less complicated. And as you can see, it's pretty easy to remember. You've got S minus A, S minus B, and S minus C. So in our case, since the sides are 8, 5, and 7, their perimeter would be 8 plus 5 plus 7, which of course is 20. So that means the semi-perimeter is 10. And that means the area of this triangle is nothing more than the square root of 10 times 10 minus A, which is 10 minus 5, times 10 minus B, which would be 10 minus 7, times 10 minus C, which is 10 minus 8. So it's the square root of 300. And lo and behold, the square root of 300, we could write it exactly as 10 root 3, or we could write it approximately as 17.3 units squared. And that's Heron's formula. Heron's formula is really, really useful when you have 3 sides of a triangle. If this is something that interests you, perhaps your final project could be on showing how Heron of Alexandria went from 1/2 base times height to 1/2 AB sine C, and then pulled out a whole boatload of trig identities to come up with the equation that you see right there.